so today we are going to wrap up our conversations about energy and work with a little topic called power. Most of you, when you hear the word power, think of a power plant or the power that makes our lights turn on. But it turns out there is a mechanical definition to power, and that's what we're going to talk about today. Before we get started, I wanted to show you your homework so that you can be on the lookout for how to solve problems like this. The first one, if it takes 10 seconds to accelerate the cart, how much power does the Kingda Ka track deliver to the 1,000 kilogram cart while it is speeding up from rest and before it starts the incline, which is a distance of 75 meters? And if you remember, the Kingda Ka is the roller coaster from the previous video's homework questions. And number two, how many watts of power does a truck with a 400 horsepower engine output? So, power, what is it? It turns out that power is the rate at which work is done. So remember, work is what is done to an object when there is a force applied to it to move it some distance. Power is how quickly you can do that. An example of that is this person jogging up the stairs. The force they have to apply to move up the stairs is always going to be just a tiny, tiny bit greater than their weight down. And the distance they move will be the same from the bottom of the stairs to the top. So the total amount of work that this jogger does is going to be the same. What will be different is the power. They can go up the stairs faster or slower. Another way to think of this is that the change in gravitational potential on the stairs is going to stay the same. Mass of the person is consistent, gravity on Earth is 9.8, and the height of these stairs is not going to change. But you can change how fast you run up a flight of stairs, and when you do that, you are changing the amount of power you have. So this is our equation for power. Power is work divided by time. And remember, we've already learned about something called the work-energy theorem. And hopefully you all know what that is by now. And the work-energy theorem tells us that the amount of work done on an object or by an object is equal to its change in kinetic energy. So if our definition of work, or power, excuse me, is work divided by time, we can also think of it as the amount of energy that was transformed over time. Your change in kinetic energy. In our SI system, the units of power are called watts. And a watt is 1 joule per second. It's how many joules of work you do per second. Watts will probably sound pretty familiar to you. This is what the guy from the electric company comes to your house and reads on the side of your house. He reads kilowatt hours. So in a sense, he is reading something related to power, but it's electric power, which is slightly different. So power is measured in watts, but it can also be measured in horsepower. And this is traditional when measuring the power of engines. So when you're shopping for a new car or a snowmobile or whatever, and it says the engine has this so many horsepower, that means it has that many units of power. It can do a certain amount of work in a certain amount of seconds. And the higher the horsepower, the faster it's going to be able to do the work. So 1 horsepower is equal to 746 watts. So a watt is much smaller than a horsepower. That's why we have the unit of horsepower, because if we were trying to give the power of an engine in watts, it would be some gigantic number. So we have horsepower that makes it much easier for us to convey, I guess, explain how much power the engine has. Power is needed for acceleration and moving something against the force of gravity. So the average power of an object can be written in terms of the force and the average velocity. And the way we do that is with a little bit of equation finagling. So we know from the first slide that power is work divided by time, how quickly you can do work. And from the first video in this series, we know that work can be defined as the amount of force, or what is done to an object when a force is applied to move it some distance. Hopefully you're all with me so far. Now this is where we make a little bit of a leap. So right now we have the equation power is equal to the force times distance divided by time. And what I'm going to do, just bring this right down here, force times distance over time, is I can actually add some parentheses here. So I have, this is the same thing as force times distance over time. Turns out it's exactly the same thing. All we did was rearranged some things. This is totally math legal here. Hopefully some of you recognize this distance over time because that is the definition for velocity. So it turns out we have many, many different ways to represent the equation for power. Power is work divided by time, or force times distance divided by time, or force times velocity, or the change in mechanical energy over time. Many, many different forms of this, but the important thing to recognize is even though you're plugging in different numbers and different symbols, they all come out to be exactly the same thing. So let me write all of those down for you. We have power is equal to work divided by time. Power is equal to force times distance over time. And all I did was plug in our equation for work. We have power equals force times velocity. And there I took the definition of velocity, distance over time, and just replaced it. And finally we have power is equal to a change in mechanical energy over time. And here I use the work energy theorem that says the amount of work that is done on or by an object results in a change in kinetic energy. So these all look slightly different, but they are in fact the same thing. We were just substituting. So let's try an example of how to solve for power. A 1,400 kilogram sports car accelerates from rest to 40 meters per second in 7.4 seconds. What is the average power delivered by the engine? And there are two ways to do this. So the first thing that I'm going to do is list everything I'm given in this problem to help me figure out which one of those four equations I am going to use. So I'm given the mass of the car, 1,400 kilograms. I am given initial velocity. It is 0 meters per second because it starts from rest. My final velocity is 40 meters per second. And the time it took to do that, accelerating, is 7.4 seconds. And I want to know what is the power delivered by this engine. So let me do a dual screen here so that we can take a look at our multiple equations. So we have a whole bunch of information here. And we need to figure out how to use it. So the very first equation we have here is a pretty good place to start. Power is work divided by time. Do we know how much work is done here? No, we are not explicitly given the amount of work done. But we are given information about the change in the speed of this car. So a change in velocity doesn't directly have to do with work. We could get there with a little bit of jumping around, but it doesn't directly have to do with it. Force times distance has nothing to do with speed. This one has something to do with speed, and so does change in energy, because remember, this is a change in kinetic energy here. So these two equations are ones that might possibly work for us because we are given information about the change in velocity of this car. And these two power equations have velocity built into them in some way. So let's use the bottom equation first. Power is equal to a change in kinetic energy over time. Well, hopefully you all remember your equations for kinetic energy. It is 1/2 mass times velocity squared. And in order to get the change, we need to calculate two different kinetic energies and find the difference. And whenever you're finding the change in something, it is always the final state minus the initial state. And then we divide that by time. So now, it's looking pretty promising, right? In order to solve for power using this equation, we need mass, final velocity, initial velocity, and time. And that is exactly what we are given in this problem. So, we can go ahead and plug some numbers in. So we have 1/2 of 1400 times 40 squared minus 0. The initial kinetic energy of this vehicle is going to be 0 because it's not moving in the beginning. And we divide by 7.4 seconds. And when you plug this into your calculator, 1/2 times 1400 times 40 squared, all divided by 7.4, we find that the power from this engine is 351. And remember from one of the first slides that we measure power in watts. So this is the amount of power in this engine. And this is one way to do it using our blue equation here, change in kinetic energy over time. However, there is another way to do it. So let me back up here, make some space on the board. If you need to go back and write that down as an example, I encourage you to do that. But we're going to use our green equation now to solve the same exact problem, but in a slightly different way. So our green equation tells us that power is equal to force times velocity. So we're going to have to do some substituting here. To calculate the amount of force from an object, we have to use Newton's second law. That tells us that force is equal to the mass of the object times its acceleration. And for velocity, we are going to have to break that down a little bit because we are given an initial velocity and a final velocity. So how do we know which one to use? Well, it turns out that this velocity is average velocity. So it's not initial or final. It is the average of the two. And we represent that with a little line over the V, over the symbol. So in order to find the average velocity of this vehicle, we can take its final velocity minus initial velocity and divide by 2. And this is going to tell us about how fast it was going the whole time. So now, it's looking a little more promising than it was before. We need mass, which we have, final velocity and initial velocity, which we also have, but we are not given acceleration in this problem. So we need one more step of substitutions. So we have mass times, hopefully all of you remember what the equation to solve for acceleration is. Its definition is a change in velocity over time. And then we multiply that by final velocity minus initial velocity, all divided by 2, the average velocity. So now we need mass, time, and velocity. A couple different velocities, but velocity. And those are all of the things that we are given. So now we can start plugging numbers in. Power is equal to the mass, 1400, times the change in velocity. And the change was positive 40 meters per second, and it took 7.4 seconds to do that. And we'll multiply that by the average velocity, which is 40 meters per second, minus 0, because it started at rest, divided by 2. And this looks really complicated, and it kind of is, and it took a little bit of algebra magic to get here. But when you plug this into your calculator, you will find that the power this engine outputs solving it this way is exactly the same answer, 151,351 watts. So it may turn out that you favor one of these methods over the other. That's completely fine. But what I want from you is to, one, be able to solve a power question when it is posed to you, and two, at least understand where each of these 4 equations came from. If you're confused about how we got here, I know it involves a lot of math and a lot of previous equations. If you are confused at all, just let me know or let Mr. Munson know, and I'm sure that he would be happy and I would be happy to go over this with you to help you understand how we got here, because it's quite important. Not only knowing what power is, but how we got there. So using this and the previous method for the same problem as an example, go back to the homework questions here and do your best to answer both of these and have them ready to be turned in next time you come to class.